Hello and good afternoon, everybody. Today we will just continue with our introduction class in minerals and rocks, and we are coming now to number 6, and this is the the classification, or we will talk about the classification. What are rocks? So what are rocks? So rocks can be classified into 3 groups. We have igneous rocks, we have sedimentary rocks, and we have metamorphic rocks. So these are our 3 groups of rocks. So therefore we have now this very nice cross section where we can find the different locations where our different rocks are formed, or an example where our different rocks are formed. So we have here 3 columns. We have here the type of rock and source material. Then we have behind here a description about the rock forming process, and here very on the right hand an example of all these rocks. So first we have here now the igneous rocks. So in the igneous rocks is described by melting of rocks in a hot deep crust and upper mantle. So actually it is so, we have a melt, and from this melt within this melt crystallization processes occur. So, and due to these crystallization processes we will then form, or it will cause, the solidification of a magma or lava. So, and a very good example for igneous rock is then the formation of a granite, and the granite that is a coarsely crystallized rock sample, which is then also called a plutonic rock. So in the next line we have then a small description of sedimentary rocks. And the sediments are a product of weathering and erosion of rocks exposed at the surface. So that means, your weathering means we have rain, that means water or ice or the wind. So, and then weathering processes will occur, and all the single sediments or mineral grains, they will become transported by ice, water or wind, and somewhere else these grains becoming deposited and buried, and then lithification processes will take place. So, and the result of such a sedimentary rock is then a cross-laminated sandstone. So then we have the metamorphic rocks, and the metamorphic rock is formed under high temperature and pressures in the deep crust and in the upper mantle, yeah? So, and therefore the rock forming processes is caused by recrystallization in a solid state of new minerals. And one typical metamorphic rock, for example, that is a gneiss, yeah? So we have then 3 different rock types. We have the igneous rocks, we have the sedimentary rocks, and we have the metamorphic rocks. So, and the metamorphic rock needs always a precursor, and this precursor can be an igneous rock, or it can be a sedimentary rock, or it can be another metamorphic rock. So in table 3.5 we have then some common minerals in igneous, sedimentary and metamorphic rocks. So in igneous rocks the most common minerals are quartz, feldspar, mica, pyroxene, amphibole and olivine. So but I have to mention that quartz and olivine never occurs together, because quartz is a very common mineral in silica saturated rocks, and olivine is a very common mineral in silica undersaturated rocks. Then we have here in the column in the middle, we have the most common minerals in sedimentary rocks. We have the quartz, the clay minerals, the feldspar, the calcite, the dolomite, the gypsum and the halite. So quartz, the quartz and the clay minerals and the feldspars, these are minerals which are silicate minerals. So, but then we can find in sedimentary rocks also other rock forming minerals like the calcite, the dolomite, the gypsum and the halite, and these minerals are non-silicate minerals. In metamorphic rocks we have also some typical minerals which I have listed here, and these are the quartz, the feldspar, the mica, the garnet, the pyroxene, the staurolite and the kyanite. So I have to mention that I have here only a selected number of minerals which are typical in igneous rocks, sedimentary rocks and metamorphic rocks. But of course, in nature we have also more typical rock forming minerals inside these different rocks. So now when we are talking about igneous rocks, we can subdivide the igneous rocks in extrusive igneous rocks and in intrusive igneous rocks. Yeah? So an extrusive igneous rock is formed when magma erupts at the surface. Afterwards it becomes rapidly cooled down due to the contact with water or air, and then it forms fine-grained ash or lava, and there we have the development of tiny crystals. So the resulting rock here, for example, that is a basalt, and the basalt is a very fine-grained rock or even has a glassy texture. Then we have the intrusive rocks. The intrusive igneous rocks crystallize when molten rock intrudes into the unmelted rock masses in the crust. Yeah? So that means the melt becomes stuck somewhere in the crust. Crystallization processes took place then very slowly, and therefore you are forming then a coarse-grained rock, and in this coarse-grained rock you have the occurrence of large minerals, like in this granite here. So, and if we are looking at this granite, then we have some typical rock forming minerals in such a granite. Yeah. So I mean, here we have the autoclase feldspar here on the left upper side. Then we have the most common quartz inside. We have a biotite inside, and we have the plagioclase feldspar inside. So, and below we have then a hand specimen of such a granite. And of course these minerals in the hand specimen look then different, yeah. And the rock that is then a naturally aggregate of minerals. So, and here in this case of the granite, We have plagioclase feldspars, autoclase feldspars, biotite and quartz. And in the picture below we have then the granite, the rock itself, how it occurs in nature. So then we have here the sedimentary rocks. First we have particles of rock, and these particles are formed by weathering, yeah. So this weathering here, it is for example the rain. So and secondly, these grains or particles of rock were then transported downhill by erosion. So and therefore we need then usually water to transport all these these particles down the hill. Finally, they were then deposited as layers of sediments on land or in the water. Yeah, we have here the deposition at the beach, we have here a delta, and then we have here the continental margin, and the continental margin we have then here the coral reefs, and we have the continental shelf. So and there they are forming then at the continental margin they are forming parallel layers of bedding. So in this number 5, these buried sediments lithify by compaction and cementation, and below this we have then here an intrusion, and we can find some metamorphic rocks there. Number 6, we have then the siliclastic sediments, and they are made of deposited particles of sand, silt and gravel. And number 7, we have then chemical and biochemical sediments, and they are precipitated from seawater or made by coral reefs and shells. So and last not least, we have here this nice picture where we can find the different locations where we form metamorphic rocks. We have here at the top, we have the continental crust, yeah. So and within the continental crust, or beneath the continental crust, we have the continental lithosphere, and there below we have the asthenosphere. And here, for example, we have the intrusion of magma, and therefore we are forming a conduct metamorphic rock, yeah? And the conduct metamorphic rock, that is, we have there just the emplacement of magma somewhere. So, and then we are heating up the surrounding rock units, and then we will form a so-called hornfels. And the hornfels is a typical conduct metamorphic rock. So then during ultra high pressure metamorphism, that means we have a lot of pressure on it, we will form, for example, an eclogite. So and the formation of an eclogite is mainly caused by plate tectonic processes. So then we have here regional metamorphism. There we are forming, for example, a mica schist, and such regional metamorphic events, that is happens in collision zones. So and then we have, for example, the high pressure, low temperature metamorphism, and that happens, for example, also in collision zones, but that is then a result, for example, of the subduction of oceanic lithosphere beneath the continental lithosphere, and there we are talking about high pressure and low temperature events. That means metamorphism as well. So in there we can subduct then, for example, oceanic lithosphere, oceanic crust, and we can also subduct the sediments. So and then it depends which type of precursor undergoes metamorphism. Then, for example, when these oceanic sediments or the sediments undergoes metamorphism, then you will form at the same pressure and temperature conditions, you will form chemically a different metamorphic rock as those ones which are resulted by metamorphism from the oceanic crust or from the oceanic lithosphere. So we are forming then always different metamorphic rocks depending on the mineral chemical composition of your precursor. Then I have here some short questions for this chapter. First, in some bodies of granite we can find very large crystals, some as much as meter across. Yet these crystals tend to have few crystal faces. What can you deduce about the conditions under which this large crystal grow? So that is now an easy question which can be easily answered very quickly. So then, next question. Which igneous intrusions would you expect to have a wider contact metamorphic zone? One intruded by a very hot magma or one intruded by a cooler magma? So last questions for this page. Where are igneous rocks mostly like to be found? How could you be certain that rocks were igneous and not sedimentary or metamorphic in origin? Yeah, that should all be very, very easily to answer, and you must just go through your slides and then you can answer it and send to me the assessment. So then number 7, we will talk a little bit, or I will introduce you into the rock cycle. So here we have, for example, a nice picture at the Middle Ocean Ridge system, at a spreading center, yes? So the rock cycle that describes then the interaction between the plate tectonic and the climate system. So, number 1, the cycle begins always with rifting and development of a divergent margin with a continent, within a continent. So that means sediments erode from the continental interior and are deposited in the rift basin, where they are buried to form sedimentary rocks. So, and here we have here the rift basin. So then you have in these small inset pictures the sediments, and you have then finally another inset which shows you the result, and that is then the sedimentary rock. Number 2, rifting and spreading continues and a new ocean basin develops. Magma arises from the asthenosphere at the middle ocean ridges and chills to form basalt and igneous rock. So then we have here, for example, we have a continental lithosphere, then we have the continental crust above, So, and here between we have then the oceanic crust. And in the middle of beneath our oceanic crust we have magma, and this magma takes place, will start to crystallize, and usually very fast because it is in contact with the water above, and then you are forming an igneous rock. So then we have here in our next slide, number 2 is the same as from before. So but number 3 is now new. We have here the subsidence of the continental margin, and this is sinking of Earth's lithosphere, and that leads to the accumulation of sediments and the formation of sedimentary rocks during the burial of them. So that means we are increasing the pressure there, and then you are forming from your sediments a sedimentary rock. That means a solid rock, and that is then formed during subsidence. Here number 3 again the same. We have the subsidence of the continental margin. We have the formation of the sedimentary rock. So and now we are coming to point number 4. We have now the subduction of an oceanic crust beneath a continent, and we are building there a volcanic mountain chain. The subducting plate melts as it descends. Magma rises from the melting plate and mantle and cools to make a granitic intrusion above. So we have here now for the second time the rise up of magma and the formation of a igneous rock, but at the beginning we made a basaltic igneous rock, and here we are making then a granitic igneous rock, which is chemically totally different from the basaltic one before. So and then we will just continue with the further closing of the oceanic basin. So and then there, when we are closing the oceanic basin, we have the continental collision, which will result in the formation of high mountain ranges. And these are at these places where continents collide and rocks are buried deeper or modified by heat and pressure. And this will result in the formation of a metamorphic rock. So and these uplifted mountains force moisture-laden air to rise, cool and condense, and precipitate. Weathering creates loose materials of soils and sediments. That erosion strips them away again. So and then we have here number 4 again, that goes then vice versa. The oceanic crust becomes then again subducted beneath the continent and building up a volcanic mountain chain. So and there we have then again the formation of a granitic intrusion. So and of course we have then again our metamorphic rock on that side. So and this metamorphic mountain belt becomes then weathered during due to snow and ice and water. So, and therefore we are therefore we have again the formation of sediments resulted in a lot of different small particles, and these were then transported again to the ocean and buried somewhere, and then the cycle starts from the beginning. So, and here we have then the summary of our cycle. Yeah, we are starting here with number 1. We have then the rifting of a continent, which is followed by the rifting and the spreading, which is continuing, and we have the emplacement of hot magma below the ocean crust, and here at the spreading center. Then we have here number 3, the subsidence of the continental margin, the sinking of Earth's lithosphere, and the accumulation of the sediments. Number 5, we have then the subduction of an oceanic crust beneath a continental crust, where we can build a volcanic mountain chain. Then number 5 here we have the formation of high-grade metamorphic rocks, and then we have again the weathering of our mountain belt and the formation of particles caused by weathering, and these particles were transported and sedimented somewhere, and then it starts from the beginning. So, and then I have again some short questions for this chapter. First question: what geological process transforms a sedimentary rock into an igneous rock? You are just watching the figures from your rock cycle, and then you should easily be able to answer it. Then you should describe the geological processes by which an igneous rock is transformed into a metamorphic rock and then exposed to erosion. So, and then number 3, using the rock cycle, trace the path from a magma to a granitic intrusion to a metamorphic gneiss and to a sandstone. Be sure to include the roles of plate tectonics, climate systems, and the specific processes that create rocks. Please, if you can do that, and send it back to me. So, and now we are coming to point number 8, the concentrations of valuable mineral resources. And that is now a very important point, especially when we are talking about the formation of ore deposits in countries like Namibia. So, what types of ore minerals do we have? We have vein deposits, we have disseminated deposits, we have igneous deposits, we have sedimentary deposits, and that's it. I mean, we have actually also some metamorphic deposits. So number 8, then, concentrations of valuable mineral resources. So we have here, for example, a very nice 3D picture. We have here again the deformed country rocks. Then we have geysers and hot springs here. Yes, that is the heated up groundwater. And below we have some plutonic intrusions. And we will now discuss the origin of vein deposits. So we have now the groundwater, and this groundwater dissolves in metal oxides and sulfides, which becomes heated up by the magma and which rises, and the precipitation of metal ores will start in joints. So, and therefore we have here then on the right hand a very nice picture from a vein deposit, yeah, that looks like this, very, very nice. So, and then we are having now typical sulfide minerals from vein deposits. We have, for example, the galena, which is a lead sulfide. We have the cinnabar, which is a mercury sulfide. We have the pyrite, which is an iron sulfide. And we have the sphalerite, which is a zinc sulfide. So, and here, for example, we have an open pit mine for a disseminated deposit of copper-bearing minerals, yeah? And most of the mines, they are open pits, and they are much easier, or people can much easier work there. It is not that dangerous and not that hot, like in the shaft, but it is a huge waste of natural materials, and you can see even these very, very big holes what they are making while they are mining from space. So, and then we have here on the left hand some examples from copper-bearing minerals. We have the chalkite, we have the malachite, and we have the chalcocite. So then here we have, for example, an igneous deposit. So, and there we have chromite, and this chromite is forming dark layers in an igneous layered intrusion, for example. So, and I think this picture has been taken from the Bushveld complex in South Africa, which is a huge chromite ore deposit. So then we are coming to the concentration of valuable mineral resources in sedimentary deposits. There we can concentrate copper, iron, and other metals. We have gold, diamonds, and other heavy minerals. And that was it just for that. And then I have some other short questions for this chapter. Back in the late 1800s, gold miner used the pan for gold by placing sediments from rivers in a pan and filtering water through the pan while swirling the pan's contents. The miners wanted to be certain that they had found real gold and not pyrite, and pyrite is called the fool's gold. Why did this method work? What mineral property does the process of panning for gold use? What is another possible method for distinguishing between gold and pyrite? I think this is now also a question which could be answered very quickly and very easily. So then we are coming to the final point from this class, the key terms and the concepts. So we talked about the anions while we were talking about atoms. We were talking about the atomic mass, the atomic number, the bedding, the biological sediment, the carbonate, the cations, the chemical sediments, the cleavage, the color. We talked about contact metamorphism. We talked about covalent bonds. We talked about crystals, and we talked about the crystal habit. So furthermore, we discussed also the features of the density, the disseminated deposits, the electron sharing, the electron transfer, the erosion, the fracture, the grains, the hardness, the hydrothermal solutions, the igneous rocks, the ions, the ionic bound, the isotopes, and the lithification. Furthermore, we talked about the luster, the magma, the metallic bond, the metamorphic rocks, the minerals, the mineralogy, the moisture scale of hardness, then about ore deposits, the oxides, the polymorph minerals, the precipitate, the regional metamorphism, and rocks. We discussed also or talked also about the rock cycle, the sediments, the sedimentary rocks, the silicate, the siliclastic sediments, the gravities, the specific gravity, the strake, the sulfate, the sulfide, the texture, the trace element, the vein, the weathering, and that's it. So and now we are through with the first PowerPoint. I have uploaded the first PowerPoint, yeah. On Moodle, you can now go through the whole complete first PowerPoint, answering all the short questions, and I will upload the next movie and the next software or PowerPoints related to the class on Thursday. Okay, see you then on Thursday, and please hand in the short questions for this PowerPoint by Friday. Okay, bye.